Hi guys, if you are viewing my channel first time, please subscribe for further updates on machine learning. Today we'll mainly discuss about a naive-Bayes classification. Naive-Bayes classification method is one of the supervised learning technique in machine learning. By using supervised learning technique, the prediction can be made. Here the mainly prediction based on the probability. Which variable having highest probability that we are selecting it as predictor. Here naive-Bayes classification is a very fastest classification technique than all other classification techniques in our machine learning. It is mainly used in real-time application like NLP text classification. So mainly naive Bayes found from the two terms naive and Bayes. Bayes naming is selected from the Bayes theorem. Bayes theorem mainly deals with the conditional probability. Okay, here I am representing one Venn diagram. Probability of A is my white area, probability of B is my gray area, and here the intersection area is probability of A intersection B. Here I am just calculating the conditional probabilities. Probability of A given B equal to probability of A intersection B, the middle area divided by complete gray area, probability of B. This is my equation 1. Probability of B given A equal to probability of A intersection B, the middle area divided by complete white area, probability of A. This is my equation 2. Okay, to get the Bayes theorem, just I am simplifying these two equations, substituting the value of probability of A intersection B from equation 1 in equation 2. Okay, I need probability of A intersection B from the equation 1, so that I will move the probability of B to the left side. So my second equation looks like probability of B given A equal to probability of A given B multiply of probability of B. This is my numerator I got from the equation 1 divided by probability of A. Okay, this is I am representing the Bayes theorem in our mathematical representation. Okay, similar way I want to represent in our machine learning terms. A I am replacing with X, B I am representing with Y. This is a way we are representing Bayes theorem in our machine learning. Probability of Y given X equal to probability of X given Y multiple of probability of Y divided by probability of X. This is my Bayes theorem. Probability of Y given X. This is my predicted for the test and new data. This is my prediction. Probability of X given Y known from the test training data. This is my training data. This is my test or new data. For the prediction, we can use the Bayes theorem. This is the theorem for the one independent variable and one dependent variable, one X and one Y. If we have, we can use this equation. For example, if we have multiple independent variables like x1, x2, x3 and so on, so that we need to expand our equation like this. Okay, the left side I'm expanding probability of Y given X, I'm expanding to probability of Y given x1, x2, x3 and so on equal to the numerator first term probability of X given Y, I'm expanding to probability of x1 given class Y equal to k multiply of probability of x2 given class Y equal to k, so on multiply of probability of xn given class Y. The first term I am expanding like this for multiple independent variables. Similar way for probability of Y, just I am representing Y equal to k. Just I am representing with Y equal to k divided by probability of x1, probability of x2, probability and so on, probability of xn. This is a denominator I am expanding like this for the independent variables. Okay, here the we know already know how the Bayes naming is coming from the Bayes theorem. Naive means all the independent variables should be independent to each other. Okay, that's why we are selecting it as naive. This is a naive term. All the independent variables should be independent to each other. There is no dependency. Okay, here naive-Bayes algorithm assumes all futures are independent to each other. Okay, that's why we are selecting it as naive. Okay, we understood how the naive-Bayes classification is formed, derived. Okay, then here the left side term, this is my prediction data. That's why we are calling it as posterior probability. And this is a likelihood, probability of likelihood. This is a first term in the numerator. Here to here, this is my probability of likelihood evidence. Probability of x1 the given class and so on. This is my probability of likelihood. The right side, the numerator, prior probability. This is my prior probability, and the denominator one is my probability of evidence. Okay, this is a mainly, this is our posterior probability. This is my likelihood. This is my prior probability. This is a probability of evidence. Okay, by using these three terms we are representing in our machine language terms. Okay, now this is a Bayes theorem we understood. Okay, now we'll take one data set for the categorical information and also continuous data. We'll take the categorical information first. Okay, here we have the categorical information. All are the categorical information. yes or no, true or false, all are the categorical, rainy, hot, high, all are the categorical information. This is my x1, x2, x3, x4. This is my plate and is my target data. Here four independent variables, one dependent variable. Okay, here by using the Bayes theorem, how we can calculate using the categorical information. We'll understand one by one here. Okay, first here we need to calculate the frequency table, and after that likelihood table. From the frequency table we can calculate the likelihood easily. From the likelihood we can calculate the Bayes theorem, the posterior probability, very easy way. And also we can calculate the new data. Okay, by using this Bayes theorem we can calculate the new data or test data. Okay, here I have the new data. By using new data we can calculate whether we are willing to play or not. Okay, this way also we can calculate the existing data. By using the existing data we can calculate the posterior probability, and also new data also we can calculate. Okay, first we'll understand how the frequency table will be calculated. Okay, here I want to calculate the frequency table, outlook versus play tennis, independent versus dependent variable. Similar way, second independent variable versus play tennis, second frequency table. Third, humidity versus play tennis, third one. And fourth one is humidity, windy versus play tennis. I have four tables, and how to calculate we'll discuss. Here outlook we have sunny, overcast, rainy. Here outlook contains sunny, overcast, rainy. We have three shades. And with respect to play tennis I want to calculate the frequency. Okay, here sunny contains how many? 1 2 3 4 5. We have 5 sunny. Here I have the total 5 sunny, and out of 5 sunny, 3 are yes and 2 are no. Okay, if you see here target data, out of 5 sunny, 3 are yes, 3 yes and 2 no. That's why I'm representing with my frequency table like this: 3 yes, 2 no. Similar way, overcast 4 and yes are 4 and no are 0. Similar way, rainy, yes are 2 and no are 3. Similar way, and if I calculate the total S 9 and complete no is 5. Total out of 14 data set, complete how many? Yes, S are 9 and no are 5. Similar way for all the cases will be same. Okay, here I know how to calculate this two table, and this one also we know. Similar way we need to calculate the frequency table for the temperature versus play tennis. We have hot contains totally 4, and out of 4, 2 are S, 2 are no. And mild contains totally 6. Out of 6, 4 S, 2 no. Similar way, it contains 4, cool are 4, 3 S, 1 no. Okay, if I calculate completely, 9 by 5. Similar way, 9 by 9 5. Okay, if I calculate how many totally, 7, and this is also 7. Okay, here high we have 3s and 4 no. Similar way, normal 6s 1 no, totally 14. Okay, similar way, windy versus platin is false 6s and 2 no, and true 3s and 3 no. This is a 6, this is a 8. Okay, similar way we can calculate 9 was 5. Okay, we know how to calculate the frequency table. Okay, now we'll calculate the likelihood table from the frequency table. Okay, here already we know the outlook, it contains 3 childs, and how I am getting the 3 by 9. Here out of sunny, it contains 3s out of 9. Here if I calculate how many yes, that's why I'm dividing with 9. 3 divided by 9, 4 divided by 9, 2 divided by 9. That's why I got this table. Okay, probability table. Similar way for the no, I need to calculate the probability. Okay, here how many no? I have 5. That's why I'm dividing with 2 by 5, 0 by 5 and 3 by 5. Okay, similar way I taken the same numerator data and denominator is 5. I got these two columns. Now how to calculate this one? How many sunny we have? 5 out of 14. This is the data we got. 5 divided by 14, 4 divided by 14 and 5 divided by 14. I got the likelihood for the outlook versus play tennis. Okay, similar way we need to calculate the temperature versus play tennis, and similar way we need to calculate the humidity versus play tennis, windy versus play tennis. Okay, I got the likelihood table and also frequency table. Okay, why we are calculating this and all means, in our backend process also, in our Naive-based backend process will be calculated similar way. Frequency table, from that likelihood table, from the likelihood table we can calculate our Bayes theorem easily. Okay, right now we'll calculate the Bayes theorem for the probability of S given sunny equal to probability of sunny S probability of S divided by probability of sunny. Okay, this is the equation. This is a formula I want to calculate sunny versus S versus sunny. Okay, probability of sunny versus S. This is the red one. Okay, how many yes in our sunny? 3. 3 divided by 9. This is my first one. I know. The second one, probability of yes. How many yes? 9 yes out of 14. That's why 9 divided by 14 divided by probability of sunny. How many sunny we have? 5. 5 divided by 14. Okay, I just calculated all the three terms from our likelihood table. See here, the first term and the second term is this 9 by 14. Why? Because how many years we have totally 9 years out of 14. That's why 9 divided by 14. And sunny already we know 5 divided by 14. I know how to calculate the posterior probability. Then I got zero point 0.6 for the probability of S versus sunny. Okay, similar way I need to calculate for the no. For the no probability also I need to calculate, right? That's why probability of no versus sunny, probability of S sunny versus no, and probability of no divided by probability of sunny. The similar way I just expanded our equation like this. And if you know probability of sunny no, here this is my 2 by 5. Sunny no, how we know already we have likelihood table. From the likelihood table, just we need to place it here. That's it, simple. Probability of sunny versus no is 2 by 5, and no, this is why no, 5 divided by 14. Okay, how many no's we have? 5 no's out of 14. That's why 5 divided by 14. And P sunny already we know 5 divided by 14 from here, green. Okay, P sunny, this is a green one. P sunny is 5 divided by 14. Okay, if I calculate the play tennis versus no probability and also S probability using the posterior, then I got zero point 0.6. 0.6 my highest probability. That's why here I am willing to play. Here S means I am willing to play. Here my probability of S is more. That's why I am willing to play whenever the sunny is S. Okay, that's why we are using the posterior probability to calculate the uh, all the probability for the prediction. That's why we are using the posterior probability. If it is zero point 0.6, that's why the playing S probability is more. That's why we are willing to play. If no probability is more, so that we are not going to play. Okay, based on the highest probability, that's why we are willing to play. Why? Because S probability is highest. That's why we are willing to play. Similar way we need to calculate the for the new data. For example, I want to predict with the new data. Outlook is rainy and temperature is cool, humidity is high, windy is true, and play whether we are willing to play or not. Okay, if I want to calculate, I already the likelihood table I have. From the likelihood, we can calculate the prediction also very easy way. Why? Because this is a backend process for the Naivebayes for the categorical information. Okay, that's why if you know the likelihood table, then we can calculate easily. Okay, here the denominator is not required. Why? Because if you do averaging, then it will be cancelled. That's why I am not calculating the for the denominator. Okay, for the denominator for the averaging, this will be cancelled. This is a constant term. Only the numerator is sufficient. Okay, here I am calculating the uh, for the S probability of S given X. Here probability of rainy with S, probability of cool with S, probability of high with S, probability of high, probability of true with S. Okay, all the four probabilities multiply of probability of S for the S for the probability of S. Okay, here I know the likelihood table so that I can calculate easily. See here, probability of rainy with S. This is my rainy with S. Already I know the probability 2 by 9. Similar way I mentioned here. Probability of cool versus S. This is a cool 3 divided by 9. Similar way, probability of high with respect to S. High means 3 divided by 9. Similar way for the true. True S means 3 divided by 9. I got 3 divided by 9. Okay, similar way, probability of S already we know 9. 9 divided by 14. Okay, if I calculate probability of S given X class, X S given X equal to probability of this is a 0.00529. Okay, this is a probability of S given X. Similar way I need to calculate probability of no given X. Probability of rainy with no, probability of cool versus no, probability of high no, probability of true no, and probability of no. Okay, this is a numerator for the base theorem. Okay, this is the probability of no with x. Probability of rainy no, this is a blue one. 3 divided by 5. Probability of cool no. Cool no means this is a no. That's why 1 divided by 5, second one. And probability of high divided by, this is a high. High with respect to no is 4 divided by 5. This is a term. And true with no. This is our probability is my 3 by 5. The last one is I got the 3 by 5. Last one probability of no is 5 by 12. This is a 5. How many no we have? 5 out of 14. That's why 5 divided by 14. I calculate the numerator for the first one and second one so that I am averaging now. Here I got the first one here divided by first one plus second one. I got zero point 0.2. Similar way, this is the numerator. Denominator I need to add the both. Here I am doing the averaging so that I got the probability for the no. I got highest probability. That's why with this combination we are not willing to play. Why? Because no versus x we have highest probability. Okay, we are not willing to play if we have rainy, cool, high and windy. Okay, we are not going to play using this combination. Okay, similar way we can predict, we have already some existing train data. Using the train data we can predict whatever the new data. Okay, using the categorical information, this way we can calculate the frequency table likelihood. From the likelihood we can calculate the prediction. Okay, then similar way if it is continuous data, for example if the independent variables are continuous but the dependent variable is always binary or categorical. For example, if the independent variables are continuous, so that we need to use this formula to convert to the frequency. Okay, here probability density function for the normal distribution is defined by the two terms, mean and standard deviation. I think this already we calculated in the previous one of the video, so that I will attach in the link how to calculate the mean and standard deviation for the data. Similarly, this is a normal distribution, the formula frequency distribution. Okay, here I have the some data here. Play golf, whether s we have the different data sets we have, and similar way with no we have some data sets. Similar way here we have s and no, right? Similar way we have the continuous data for the humidity and also continuous data for the no. Okay, similar way here I am calculating the mean for the this complete data and also mean for the this complete data no data. And also here I'm calculating the s with respect to the complete standard deviation, and also complete this data I'm calculating the standard deviation. Okay, I know the standard deviation for the s and also no, so that we are willing to calculate easily. Okay, using the Naive-Bayes algorithm for the continuous data we should use this formula in our backend process. If the independent variables are continuous, then we need to use this formula. This is a backend of the Naive-Bayes algorithm. This is a probability of humidity is 74, play willing to play or not. Okay, here I am using the same formula. I know the already standard deviation 10.2. This is a 79.1 is my mean. Okay, using this two I am calculating the my probability. Okay, I got highest probability than this, so that we are willing to play whenever these humidity conditions are like this. Okay, play no, if I calculate I got the less prediction than this, so that we are willing to play when we have this type of willing to play we have s or many. And also if we got the highest probability, then we are going to play whenever we have the data like this, so that we can predict with our new data also. For example, if they have given the new data, so that we can calculate easily. Okay, once we have the already we have the formula, so that we can calculate easily. Okay, using the continuous independent variable, so that we need to use this one. If it is categorical information, so that we need to use this way. Okay, similar way we can practically we can execute the naive base using the one of the data set. Okay, here I have the one data set. It contains kyphos is my target data, y data, and age number independent data. Okay, for the categorical independent variable, so that it will be used this formula to calculate the prediction or the training data for our naive Bayes algorithm. It will be used these formulas. Okay, why? Because my independent variables are continuous, that's why it will use the second example. It will use the first, it will calculate the main standard deviation, from that the normal distribution. Similar way we'll be calculating here. Okay, we are using the Jupyter lab, will be executing, will divide the training data and also test data. Okay, here I have the kyphosis is my target data, x1, x2, x3, age number, start. Okay, I am dividing into the first two sets. One is my training set, is my up to 56 samples I am using for the training set, and the remaining samples 30% I am using for the test data. Okay, here if it is y column, I am representing with the y train. If it is x column, this complete green area I am representing with x train. Similarly, if it is y column, y test. Similarly, this is a y test. This is a x test. This is my x test. Okay, I know all the possibilities here. I know the test train data. By using the x train and y train, we can train the model. By using the x test, if we pass the x test, then we'll get the y prediction. Okay, once we have the y prediction and y test, then we can calculate the accuracy of our model is very easy way. Okay, this is a way we can train and split. First we need to split the data. After the splitting, we need to pass the y train and x train to train the model. After the training, we can pass the x test, we'll get the y prediction. Then we can compare this y test and y prediction, then we can calculate the accuracy. Similar way, I'm using the Naivebayes in the Jupyter lab. Here import pandas as pd. This is my pandas. This is my alias name. I'm using the pandas for the excel operations and also some metrics display confusion metrics. Here my data set, importing the data set equal to, this is my variable equal to pd is my alias name of the pandas, and this is my method read csv, and just I am passing my kyphosis csv here, so that head dataset dot head, it will display first 5 records. If I open the dataset, it contains kyphosis age, number and start, and absent, absent, present. Okay, same first absent, absent, present, and it contains 4 columns. Okay, here it will display the first top 5 records, absent, absent, present. If you see here, you will be able to see the same absent, absent, present. Okay, same data I'm able to import here using the read csv, and after that I'm displaying whether I'm accessing the correct one or not. And the data processing, okay, here I need to treat kyphosis as my y data, and the remaining all other I am dropping the kyphosis, and the other parameters I am accessing to x. Age, number, start, here I am printing the x value first. Age, number, start my data, and the last one is my y data is my kyphosis. Y data is my kyphosis. Okay, this is my y. I am treating it as pre-processing, data pre-processing. I'm representing it y, this column. This is my complete y. This is my complete x. Okay, now I need to divide into the 4 sets, how we were divided in the excel, right? Similar way I need to divide here. Okay, here I'm using the one of the sklearn package. Here I'm importing sklearn test and train test split. This is a method. It will split the data to the 4 parts. Likewise, we split it here, right? X train and y train and x test and y test. Similarly, I'm dividing into the 4 parts. Test train test split. I'm passing the what is the x and what is the y. Already we defined what is the x and y. I'm passing that two values here. And test size, I am mentioning it here. Already we discussed 70% of the train data and only 30% of the test data. Okay, that's why I'm mentioning the same here. Random state, here I'm mentioning 10. If you are not mentioning anything, the always the prediction will be always changing. That's why I'm mentioning the random state is 10. Then always it will take the same sample data for the test data. Okay, that's why always we need to mention the random state. Okay, now I got the x train and x test, y train and y test. I got the 4 samples like we discussed in the excel. Okay, I got the 4. Okay, then we can train our algorithm and also test using the Gaussian Naivebayes. This is our Gaussian Naivebayes. Will be calling it as Naivebayes algorithm. This is I am importing from the sklearn Naivebayes import Gaussian NB. And here for the confusion matrix also we can use the sklearn, and also we can use numpy also we can use, or import pandas also we can use. Okay, here I'm calculating the sklearn. I'm importing the accuracy and confusion matrix calculation. I'm using the sklearn. Here this is my object I'm creating. I'm accessing my class Gaussian Naivebayes. Okay, creating my just I'm creating my object. I'm accessing my class. Within the class I'm calling with my fit. This is my method to train the model. Okay, this is my object dot fit is my method. I'm passing the x train and y train. Okay, this x train and y train I'm passing to the model, so that the model training is done. Okay, the model training is done, so that we can predict. The same object I'm using dot predict is a method, so that we can pass the x test, then we'll get the y prediction. X test I'm passing, then we'll get the y prediction. Okay, now I got the y prediction. Okay, I got the y prediction, and also y test we know already. Okay, already we know y test. then we got the y prediction. Then we can calculate the confusion matrix. From the confusion matrix we'll come to know how many predictions are correct, how many predictions are wrong. Okay, here the confusion matrix I am using the pandas. PD is my alias name, that's why I am using the pandas here. I'm using the cross tab function. I am passing the y test and y prediction. Okay, here I am passing my y test and y prediction here, y test and y prediction, these two. To calculate the accuracy or confusion matrix, we need to pass the y test and y prediction. Here row actual data is my rows, this is my actual data, this is my prediction data is my columns. Okay, here I'm using the seaborn package for the heat map. Okay, here I'm passing my confusion matrix here to display whether here in the graph format, so that I'm using the heat map here. Okay, this is my actual data, this is my prediction data. For example, actual is S and prediction also S. For example, actual is absent and prediction also absent. Okay, this is a correct prediction. And actual is present and prediction also present, this is also correct. Okay, these two predictions are correct. Even the actual data and predictions also correct, and these two metrics are wrong. For example, see here actual data is present but I am predicting with absent, this is a wrong. And similar way actual data is absent, I'm predicting with present. Okay, this is my prediction column. Columns are prediction. Okay, here this one black one and this black one also wrong prediction. Out of this is 50 30 15 20, out of 25 20 are correct and 5 are wrong. Okay, 20 by 25 if I calculate, then I will get the accuracy of 0.5. Here I'm using the accuracy score, my sklearn API. Here accuracy score I am using. Okay, accuracy score I am passing y test and y prediction, then same way I am passing the same data, then it will be calculating the accuracy. Simply it will do 20 divided by 25, then it will calculate the accuracy, then we'll get the 0.85 0.8. Okay, this is a way we can use the Naivebayes algorithm to calculate the accuracy and also prediction, and whether we can use the our for our future use or not. Based on our prediction we can identify whether we can use or not. Okay, thank you friends, thank you for watching. If you like the video, please share. Thank you.